Today we're going to be talking about lift and drag with reference to the coefficient of lift, coefficient of drag, and the lift-drag ratio in association with the angle of attack, which allow us to explain the meaning of the word best lift-drag ratio for the best glide range, the maximum lift as we approach towards a stalling angle, and minimum drag, which is a maximum level flight speed. So in order for us to do this in a meaningful way, we have to go back to our basic concept of flight and the theory of lift. So if we go back to here, our very basic, we have an aeroplane here. There are four forces that are acting on an aeroplane, which are lift, which is an aeronautical force acting upwards to the sky. We have what we call weight, which is a physical mass of the aircraft due to gravity. Then we have further two forces, which is a thrust based on the propeller of the aircraft or the jet engine. And opposing that is, of course, the drag. So we have to have a clear understanding of how lift is generated, how drag affects the performance of the aircraft in relation to the angle of attack. Okay, for us to start, we will look at the aerofoil in detail. The aerofoil is an aircraft wing in cross section. You will see that the front is the leading edge. The back is called the trailing edge. If we were to draw an imaginary line from the leading edge to the trailing edge, we have what we call a chord line. Okay, so we have this aerofoil in the air. An aircraft that flies through the air is called the flight path, and the air flowing around the aircraft in parallel but in opposite direction is called the relative wind. So having these two facts and the understanding or the pictorial diagram of the angle of attack where it might be, we can deduce that the camber and the aerofoil shape, which we talked about just now regarding the chord line, and in relation to the relative airflow of the flight, you will see that the angle represents what's known as the angle of attack. So having these terms out of the way, we can go straight to the gut of it all, which we are looking for is the creation of lift or the production of lift. In order to understand the production of lift, there are two laws that comes into effect. First is the Newton's three laws of motion, which they all apply, but particularly the third law of motion. Then the other one is what's known as the Bernoulli's principle, which you're all familiar with. The Newton's third law of motion states that for every action there's an equal opposite reaction. So if you were to imagine driving in a car and you stick your hand out and then you tilt your hand, the air that's coming, hitting your palm and forcing it to go up, it's the force that is pushing up your hand. So similarly, that's where the third law of motion of Newton's apply. So moving on quickly to Bernoulli's principle, it states that as the velocity of the fluid, in this case air, increases, its internal pressure decreases. That can be shown by this Venturi effect here. So in the very beginning, the entrance, we have a known velocity and pressure, constant velocity and pressure, that air is flowing through here, and as the venturi or the pipe narrows, it's forced to increase in airspeed, which creates a pressure reduction and increase in velocity. Of course, on the other side, it goes back to the normal of pressure and velocity. So if you can imagine this venturi with the curvature where it's forced to accelerate, similarly can be applied to this camber of a wing aerofoil in this state. Having that camber shaped, air on top has to move faster in order to create this pressure of low area. So therefore, the aerofoil typically has a flat base and a camber, which is the top surface, where the air flows faster based on the Bernoulli's principle, creates a low pressure, and bottom remains as high pressure. So we all know from science that the air pressure, the gradient that has been created, the air moves from high pressure to low pressure. Hence, we have this force, aerodynamic force, where the wings are literally sucked up or pushed up into the sky. Okay, so having understand these laws, we come to what we have called the lift equation. So we do need to understand this. That way it's easy to explain the coefficient of the lift based on this lift equation. Basically, the basic lift equation is half of the density surface area of the wing with the velocity of air squared with the coefficient of lift. Okay, so these are the numbers that's been crunched up. We can go into detail, but rather than that, we need to carry on further with the understanding of the coefficient of lift. Before we do that, we can go and talk about drag. Okay, so here we have two types of drags, which is the parasite drag and the induced drag. Parasite drag comprises of form drag, interference drag, and skin friction drag. Okay, so form drag is when the boundary layer separates. Okay, for example, you have on the aircraft drain holes and so forth. It separates from the boundary layer. Interference drag basically is caused by the mixing of the boundary layer of airflow at junction of, for example, wings, fuselages, nacelle, and so forth. Then we also have the skin friction, which is determined by the total area surface of the aircraft, which is exposed to the air flowing past it. So, next, if we look at the parasite drag, it is proportional to the square of the indicated airspeed. In other words, if you have a chart showing the speed of the aircraft that's being flown and the parasite drag, as you fly faster, basically the parasite drag quadruples. It becomes 4 times as much parasite drag. It would be like imagining an aircraft flying at 120 knots. It will have 4 times the parasite drag than an aircraft that's flying at 60 knots. Okay, so that's quickly touching on to the parasite drag. Let's talk about induced drag. Induced drag, well, basically, induced drag is a result of the aircraft when producing lift. So we have a wing where at the wingtip vortices are created, which causes or the changes in the downwash angle of an aeroplane, which then tilts the direction of the lift. Usually it's perpendicular lift, force that is right up, straight up. And when you increase the angle of attack of an aircraft, what happens is induced drag becomes greater due to the fact that the vortices are causing the changing the downwash angle, and that's resulting in the directional lift going backwards and from a vertical to a slightly out. So the slower the aircraft, the higher the greater angle of attack, then you're having a induced drag becomes much higher. Alright, so we have the drag generally explained to you that are acting on the aircraft. Now if we go back to the lift diagram that we just gone through, you will find that in the lift equation, there are factors that affects in the lift equation that determines the coefficient of lift. Some of them are the 4R angle of attack, the shape of the aircraft, the Reynolds number, and they call the Mach number. Of course, you can go into much detail of this, but I only have limited time. So if you were to see a graph that is drawn here with the coefficient of lift values and the angle of attack, you find that when you change the angle of attack, if you have an angle of attack that is in the negative range, you have a coefficient of lift in the negative. But as the angle of attack increases, it coefficient of lift figure starts to increase as well. So here we have an increase in the angle of attack in such a way that the coefficient of lift starts to increase as well until such a point it reaches approximately 15 to 16 degrees, where it becomes critical and it becomes a stalling angle, where it becomes turbulent. It can no longer maintain the lift. Even though it's still continuing to maintain that lift, the drags become so much higher and the coefficient of lift just starts to drop. Okay, so if you look at this lift equation with all the formula depicted here, is based on, of course, the kinetic energy. And we have these units here that will derive the amount of lift that's been generated by a particular aerofoil. So the coefficient of lift depends on the angle of attack, and also it depends on the shape of the aerofoil. For example, you have this shape here. It gives you a value, a coefficient of lift of 1.15, where you have a symmetrical aerofoil, which means that the aerofoil top and bottom are the same, therefore the pressure remains the same, there's no lift generated, so the coefficient of lift is almost zero. So you see the angle of attack here and angle of attack here. So if you have a shape that has a leading edge radius, a large leading edge, which is a fat camber aerofoil, then it affects the coefficient of lift at or near the point of the stall area, but it gives a more progressive stall. That's why hence this graph shows a progressive stall rather than a thin camber wing which will stall more or less immediately. So these are the shape that determines. So it's the shape and the angle of attack. Alright. The other thing that affects the coefficient of lift depicted on the graph here is the aspect ratio, as well as also the camber. So if you look at this first graph here, you'll see the coefficient of lift drawn with the angle of attack. You notice here that we have a symmetrical aerofoil we just described just recently, which has a similar shape, the top and bottom, creates a similar pressure, so there's no coefficient of lift is at zero. So symmetrical section has a coefficient of value of 0 at the angle of attack 0. Here's the angle of attack. As we increase, there's a coefficient of lift that's increasing for a symmetrical section. However, if you have an increasing camber, if you like a big fat wing, then what happens is, if you see that, it's already giving the coefficient of lift with even negative angle of attack, but as it becomes positive and positive, it increases in the coefficient of lift. So these are the factors that are affecting the coefficient of lift of an aerofoil. The other one is the aspect ratio. So aspect ratio is basically the wingspan of the aircraft and the width. So you can compare it to, imagine, to a glider and a Cessna 172. So if we have here a graph with a coefficient lift drawn with the angle of attack, based on the aspect ratio, the aspect ratio of this wing, which is A2, will be less. With aspect ratio is a less aspect ratio than the A1. So what happens is that a low aspect ratio wing produces greater downwash, right? Which is due to the tip vortices being close together, and therefore the lift of a low aspect ratio, which is, for example, a Cessna 172 wing, will increase less rapidly. So it's a shallower graph than, for example, a glider, which gives you a more increased coefficient of lift than the low aspect ratio wing, like the Cessna 172. Alright. Of course, there are other factors which are also affecting the coefficient of lift. One of them is Reynolds number. If everybody's heard of the Reynolds number, which basically tells you that it's a relationship between the speed of a flow of a fluid and the diameter of a pipe. So here we have a graph again with the angle of attack versus the coefficient of lift. The effect of Reynolds number on the coefficient of lift. There. The Reynolds number applies to the airflow over a wing, which affects the value of the coefficient of lift. For example, an increase in the Reynolds number here, which is an increase, will give a greater value of the coefficient of lift. So that's just tested and scientifically found out that the Reynolds number increases the coefficient of lift. The other one we talk about, not much in detail, is the Mach number. Obviously, the high-speed performance aircraft have a thinner camber wing aerofoil, and it's usually swept back. So coefficient of lift of is less for a swept wing than one without the sweep for a specific angle of attack. So as you see, the angle of attack increases. Obviously, the coefficient left is at a lesser rate than if it would be for a straight type of a wing. Okay, so that we have all the explanation of that factors that affect the coefficient of lift. Going back to the drag, which we talked about before, the parasite drag and induced drag, which becomes now the total drag that is acting on an aircraft or an aerofoil. So if we have a graph to depict that, you will see the airspeed this way increasing and drag increasing this way. If we were to plot the parasite drag, like we said, is that as the airspeed increases, so does the drag. Whereas the induced drag decreases if you increase the angle of attack. All right. So which means if you go slower with airspeed, in order to go slower, you got lifting devices and you increase your angle of attack, the induced drag becomes greater at lower speed. So the parasite drag varies with the square of the indicated airspeed, and also induced drag varies inverse to the square of the indicated airspeed. So the minimum drag speed, it's a speed for maximum lift drag ratio, falls in this what you call the total drag curve. This is a total drag curve giving where the parasite drag and the induced drags meet. So this is a minimum of the drag that you want between the two drags. So that will what we call the best lift drag ratio, or the maximum lift drag ratio, which is the most efficient speed for any particular aircraft. Okay. In order to explain that more in a graphic, in a pictorial world, it's best known as the best glide speed. When you have the best lift drag ratio, for example, for Cessna 152, that speed will be 68 knots. So if you have an engine failure, that's the speed you aim for. It gives you the best lift and drag ratio that gives you the greatest distance that you can achieve. All right. So finally, we look at this graphs that shows the relationship of angle of attack and the coefficient of lift. Okay. Second final graph we have here is the angle of attack versus coefficient of lift, coefficient of drag, and coefficient of lift drag. All right. So you notice here that we've talked about it, that if you increase the angle of attack, the lift increases more and more, and what happens is it gets to a point where there's a critical angle called the coefficient of lift maximum is achieved around 15 degrees. Then everything, the boundary layer, everything breaks down, becomes turbulent. Even though it's creating lift, it's no longer sustaining aircraft in the air, so the weight takes over. So that's the coefficient of lift max graph. Then we have what you call the graph where it's called the coefficient of drag. So as the angle of attack increases, the drag also increases it. Then when you have a lift drag ratio, is that from 0, as you increase to such an angle, there's an optimal angle at where you have a lift and drag ratio is at its maximum. Then as you further increase the angle of attack, the lift drag ratio becomes less and less. So this is the way you have the maximum lift drag ratio, or what we call the maximum lift drag ratio is approximately 4 degrees, which is less. Usually it is less of an angle than maximum lift. Obviously you have to lift up your aircraft to maintain the maximum lift, which is approximately around 15 degrees. So that summarizes basically the efficiency of an aircraft, which is determined by the comparison of basically the output, which is the lift, and which needs to overcome from the four forces the weight of the aircraft, and the input, which is the thrust being applied, is to counter the drag working in opposition to the thrust. So the efficiency of the airfoil, the lift drag ratio, depends on the angle of the total aerodynamic reaction to free stream flow. So that more or less that graph sort of gives you an idea of how all these things work together. One final point which I like to touch base is that the modern aircraft dictate that there's a need for minimum drag. So it wants to fly with a minimum drag for costs of fuel and so forth, savings. So the designers usually use an aerofoil section that gives the lowest parasite drag at the cruise angle of attack. which means that it attempts to maintain a laminar boundary consistent with the flow, so as long as possible, and to reduce the surface friction drag. Okay, so these angle of attack are low, which means that the angle of attack are usually low, not high, because the drag will become more excessive. So you have what they call a favorable low drag range that the manufacturers try to aim for. Okay, and also it's also known as a laminar or the low drag bucket. Here's a bucket that for a symmetrical section graph that's been shown with the coefficient of drag versus coefficient of lift. So this is the bucket you're looking at, and the most efficient between the coefficient of lift and with drag is this area here where they make the design for this type of aerofoil which is fixed to the aircraft. So in conclusion, if we understand function of the lift, how it's generated, the laws involved, and the coefficient of lift, which is a function of the lift equation, then you have a better understanding of the performance of the aircraft. Thank you very much.